Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Welcome back. Problem 7.1, and this is chapter of transverse loading. So the statement is, if the wide flange beam is subjected to a shear of 20 kN, determine the shearing stress on the web at A, indicate the shear stress component on volume element located at this point. So you can see this is a wide flange beam. The shear force that is V is given as 20 kN. All the values of this cross-sectional area of the wide flange beam is given. This is the width of this flange. This is total height. This is the thickness of web, and you have been asked to find the shearing stress component at point A and also determine the shearing stress at this point A. So let's start with the solution. So as we know that shearing stress in this beam is equal to V into Q divided by I into T. Now what is tau? This tau is shearing stress in the member at the point located at a distance of y dash from neutral axis. This V is the internal resultant shearing force or the given shearing force. This Q is the first moment of inertia, and you will see how we will calculate. I is the moment of inertia of entire cross section of this beam, clear, and T is the width or width of the section. So this we will use this formula in order to calculate this shearing stress. So first step, we have B, we do not have Q, we do not have I, we have T as well, clear. So first of all we will find the second moment of inertia I for this whole cross section of the beam. So the moment of inertia, of the cross section about neutral axis is, you can see this is 300. The height of this web is 300, so neutral axis will be the mid of this 300, clear. So this is your neutral axis. So if I draw half section of this beam, so let me draw it first. So for example, this is the flange and this is the half of the web, clear. You can see the width of this flange is 200 meter, so I will represent it in term of meter. So this is 0.2 meter from this side to this side. This is 0.2 meter. The thickness of flange is 20 millimeter, so this thickness is in term of meter, it is equal to 0.02 meter, clear. Also you can see the from this flange till the mid of neutral axis, this distance will be 300 divided by 2, which is equal to 150 millimeter. So this distance will be equal to 0.15 meter, and this will be your neutral axis. Neutral axis passing through centroid, passing through centroids. That is why it is called neutral axis or centroidal axis as well, clear. And this is the point A where you are interested to find out the shearing stress at the web. So again you can see this area will be equal to A dash. This will be A dash. Why? Because you will find Q, and Q is equal to Y dash bar into A dash. I will show you in a while. First let me calculate this, the moment of inertia. So you can see that moment of inertia I is equal to, for rectangular section, that is equal to, for rectangular, this is equal to, I is equal to 1/12 BH cube. Clear? BH cube. So this section is not rectangular, so if I consider it as rectangular, so I will draw a dotted line. So this hole will be a rectangular. Clear? And that is equal to 1/12. B over here is equal to, you can see, 0.2. So 0.2, and height is equal to, total height is equal to 0.1. Total height is 0.34. Okay, so as I is the whole, for whole cross section, so you can see if I draw it as a rectangular box, so this is width, which is 0.2 meter, and total height is 300 plus 20 plus 20, which is equal to 340 millimeter, and in term of meter it will be equal to 0.34. so total height is equal to 0.34 whole cube. But this is for rectangular. So if, what if I subtract these portions, this portion and this portion, so I will get the moment of inertia for this I-type shape. So I will, what I have to subtract is, I have to subtract minus 1/12. Again, this is also a rectangular portion, so its height is 300 millimeter, which is equal to 0.3. This is cube into its width is equal to 200 minus 2 times 200 minus width of the thickness of this web, which is 20 millimeter. So 200 minus 20 is 180 millimeter, and if you divide it by 2, it will be, this width will be equal to 90 millimeter. Okay, so 90 millimeter is again 0.09 meter. So this is B, this is height, minus again this portion, which is same like this. So I will write minus 1/12. B is 0.09 and height is 0.3 whole cube. So when you calculate it, you will get the moment of inertia of whole beam is equal to 0.250 into 10 raised to power minus 3 meter power 4. Now we have I. We will calculate this Q, and for Q we will draw the half section of this beam. So we know that Q is equal to Y dash bar into A dash. Now what is A dash? A dash is this area where you are going to find the shear stress. Clear? And what is Y dash bar? So Y dash bar is distance from neutral axis to the mid of this section. This is Y dash bar, or you can say Y dash. Clear? Okay, so what is the value of this Y dash bar? So if you divide 0.02 by 2, you will get this half distance, which is equal to 0.01, and this 0.15. So it will be equal to 0.16. So Y dash is equal to 0.16 meter. And what is A dash? So A dash is the area of this cross section, which is 0.2 into 0.02. So we will calculate this QA, first moment of inertia of this section, about neutral axis is y dash into a dash. So y dash is equal to 0.16, clear, and a dash is area 0.2 into 0.02. 0.2 into 0.12, 0.2 into 0.02. So when you calculate it, you will get this QA is equal to 0.64 into 10 to the power minus 3 meter cube. Now you have I, you have Q, you have B, and you have T, and T is the width of this cross-sectional A dash. So you can put it in this formula to get the shearing stress at point A. So shearing stress is equal to V into Q divided by I into T. So V is given as 20 kilonewton, 20 into 10 to the power 3. Q is this one, 0.64 into 10 to the power minus 3. There, I is the moment of inertia of whole beam, which is 0.250 into 10 to the power minus 4, and T is the width or thickness. So this is the thickness. Sorry, this T is the thickness. Clear? So 0.02. So when you calculate it, you will get this shearing stress is equal to 2.559 into 10 to the power 6 Pascal, or that shearing stress at point A is equal to 2.56 megapascal. So this is the shearing stress at point A. Now if you are going to draw it on this element at this, let's say I am going to draw it on the element portion to show this shearing stress. So let's say this is the element, clear. So this is point A. So at this face the shearing stress will be this one. This will be the shearing stress, and on bottom surface it will be like this. On top surface this shearing stress will be like this, and on the opposite of this surface the shearing stress will be like this, and this is equal to tau A, which is equal to 2.56 megapascal. So I hope you have enjoyed this video. Thank you for watching.